Okay, so hi everybody and welcome to this Earth Sciences Research Group seminar. My name is Janine Kavanagh. I'm a lecturer here at the University of Liverpool, and we're delighted to welcome you all to our first live stream YouTube seminar of the series. And I'll just introduce Caitlin Chalk, who's going to introduce our speaker. Thanks, Caitlin.
Yeah, hi, thanks for coming everyone. So today we're hearing from Dr. Andrew Pimm. And Andrew is a research fellow in the School of Chemical and Process Engineering at the University of Leeds, where he works on a wide range of applications related to energy storage and renewable energy. His background is in mechanical engineering, which he studied for his undergrad degree at the University of Nottingham. And he stayed at Nottingham to do his PhD, where he designed flexible fabric energy bags to store compressed air energy underwater. And since then, Andrew's worked on projects such as modelling the energy demand within cities and also designing floating offshore wind turbines. But today, Andrew is going to talk about his current research area, which is on decarbonising the UK steel industry from both a technology and policy perspective. So over to you, Andrew.
Thanks, Caitlin. I'll just share my screen. How's that? Are you getting that full?
Yeah, it looks good.
Okay. Yeah, so yes, first of all, hi everyone. Thanks, Janine and Caitlin for having me and for hosting this. Yeah, so as Caitlin said, I'm going to be talking to you today about my research on decarbonising the steel industry, focusing on the UK and looking at different technology and policy options. So I'll just initially, there we go, tell you just a little bit about myself. So as Caitlin said, I did a degree and PhD at the University of Nottingham. My PhD was focused on underwater compressed air energy storage. And you can see a couple of the bags that we ended up testing towards the end of my PhD and the start of my postdoc work shown here. So yeah, the idea there was storing energy at large scales by compressing air and pumping it into bags anchored on the seabed. I then worked also on adiabatic compressed air energy storage, like looking at thermodynamics and economics, some hybrid storage systems involving different combinations of storage technologies. I then moved to the University of Leeds in late 2015 to work on a project on decentralized energy storage. Also worked on projects looking at generation integrated storage and the impact of storage operation on grid CO2 emissions. And then about a year ago, kind of moved into industrial decarbonisation, focusing on the techno-economics of decarbonising the steel industry. So yeah, there you go. So just quickly, the structure of the presentation today. I'll first of all give you a bit of an introduction to steelmaking in the climate and some traditional, well, what the existing kind of approaches are to steel production, and then look through a few of the kind of key options for deep decarbonisation of the industry. So they're biomass, carbon capture and storage, CCS, and then hydrogen direct reduction of iron. And in that, focusing particularly on the research that I've been doing over the last year. I'll lay out some of the policy options available to decarbonise in the UK, particularly provide some views on new coal mines, or particularly Woodhouse Colliery in the UK, and then present my conclusions. So yeah, first of all, steel and the climate. So amongst the heavy industries, steel production is the sector accounting for the largest share of CO2 emissions, and it actually accounts for about somewhere between 7 and 9% of the figures that I see of global emissions. energy consumption for steel has been increasing considerably over the years. So in the last 30 years, energy consumption for steel production's doubled. And it's really a highly energy intensive business. So yeah, bringing down the energy requirements is really key. And the demand for steel is expected to increase as we further decarbonise. So in terms of the global demand and where steel is used and produced, there's a figure here showing you in terms of, on the left you can see MT per year, so megatons, millions of tons per year. The blue bars being capacity, grey being actual production, and yellow apparent steel use. You can see that China accounts for more than 50% of the world's steel production. So an awful lot of the steel that is used around the world is being produced in China. And then in terms of kilograms per capita being shown on the right hand side here, you could see that it's particularly high in places like Korea, Japan, the US, and China as well. And we'll kind of look into that in a sec, well, here. So thinking about what the future demand is likely to be for steel then, well, it's known that steel stocks rise in any given country. The stock of steel in that country per capita rises with GDP per capita, up to what's known as the saturation stock, which is around, seems to be around 12 tons of steel per person in countries with high levels of GDP per person. You could see this being shown on the figure, the lower left here, particularly, so you could see kind of Japan, Canada, US all getting to around 12 tons of steel per person in recent years as GDP per person has increased. And so this kind of understanding of saturation stock combined with the expected kind of increase in GDP per person as countries develop, and also expected changes in population, allow researchers to predict what will happen to global steel demand. And you can see at the lower right here, in terms of steel output since the 60s, what's happened up to now, and then what is projected to happen in terms of steel output going forward to 2050. You could see that steel production is expected to increase. And you can also see a split here between what's being produced from iron ore and what's being produced from scrap recycling. So looking then at what the production routes are for steel. So we can broadly break it down into primary production and secondary production, where primary production is taking iron ore, converting that into iron, and then ultimately into steel. And secondary production means taking scrap steel and then using that to generate, produce new steel. So the key aspects of this then are the iron making stage shown in the central kind of column, and then the steel making stage. So in terms of iron making, what's typically used to the highest level worldwide is the blast furnace. And I'll explain in more detail in further slides, but essentially you take iron ore, which is iron oxide, and you need to get that into pure iron. So you remove the oxygen by using carbon from coal. So you convert coal into a concentrated form, which is coke, by heating it up in a coke oven, and then you mix the coke with the iron ore, so your iron oxide in a blast furnace, raise it to very high temperatures, and the carbon from the coke reacts with the oxygen, leaving you with pure iron. You then, to produce steel, you need to reduce the carbon in there, because you're left with a high level of carbon, and also get a small percentage of so you do that using oxygen, and then potentially also add other elements for producing certain alloys. So yeah, there's the blast furnace. There's also DRI, which is direct reduction of iron, which is a different type of furnace, which again I'll cover. And then in terms of steel making, there's the basic oxygen furnace, where you blow oxygen through. There's the electric arc furnace, which it uses an electric arc, as is suggested, so high current, and then open hearth furnace, but that's really not used very widely. And then just covering quickly the UK steel industry. So UK steel production has declined considerably in the last 50 years. It's currently about 7 million tons per year. But as you can see in the figure at the bottom right here, it's shown in orange, you can see back in the kind of late 60s, early 70s, production was much higher at something like 25 to 30 million tons per year. So there's currently 2 large integrated steelworks in the UK. One is in Scunthorpe and one is in Port Talbot. These produce steel from iron ore using blast furnace basic oxygen steel making. So it's that combination of the blast furnace for getting to your pure iron, and then the basic oxygen furnace for producing steel. It's highly reliant on coal, and has very high levels of CO2 emissions. These steelworks have very high output, so they account for the vast majority of those 7.2 million tons. They use fairly small quantities of scrap. We also have secondary steelworks in South Wales, Sheffield and Rotherham, and these produce steel from much higher levels of scrap using electric arc furnaces. And yeah, lower output, much higher scrap charge, and because they're electrified, so using electric arc furnaces, there's the potential there to use low carbon or zero carbon electricity. And then in terms of kind of what's been happening in recent years, there was the Redcar Steelworks in Teesside, closed in 2015. Chinese company Jingyi acquired British Steel in 2020. And then, as you've no doubt heard in the news recently, Liberty Steel is really in crisis, and we kind of wait to see what will happen there. So yeah, just to then cover the traditional approaches to steel making. So there's a kind of a schematic here of hopefully it doesn't change, there we go, schematic here of a blast furnace, which is, as I said, used to reduce iron ore, iron oxide, to pure iron, which is known as hot metal. So coke, as I said, a concentrated form of carbon derived using coal, is used to provide heat up to something like 2000 degrees C, and it also acts as a reductant. And the chemical formula given here kind of shows you what happens in terms of iron hematite, Fe2O3, which is your iron ore, plus carbon monoxide gives you iron and carbon dioxide. So yeah, as I said, very high levels of CO2 emissions. They have so blast furnaces have very long campaign lives, very long campaigns, so typically greater than 15 years between services, and you can't stop them operating. They basically start operating and that's it. They keep running for 15 to 25 years. And if you did try to stop them from operating, then it would be potentially very expensive. So yeah, it's a very much a big investment. These are 10 to 15 meters tall. So they're big kind of beasts. I think there's like two in South Wales at the steelworks there, and then similar number, maybe 3 or something currently operating in Scunthorpe. So it's possible to replace some of the coke with biomass, so using the carbon in biomass. However, this option is limited by the compressive strength of the biomass. So part of the mix of coke and iron ore in a blast furnace is known as the burden, and part of the job of that actually is to hold the whole thing up. And if you try to replace all of the coke with something of a lower compressive strength, then it simply wouldn't be able to operate in the same way. So yeah, that's the blast furnace. You get hot metal out, which is effectively pure iron or carbon-rich iron. So you then need to reduce that the level of carbon down to a small percentage to give you steel. And this is done at large scale using the basic oxygen furnace. So oxygen is high purity oxygen is injected into the kind of liquid iron. This ignites the carbon which is dissolved in there, forming carbon monoxide and carbon dioxide. So again, more carbon dioxide emissions. So lime is used to absorb impurities, forming slag, which is removed. Scrap is also inserted in there. Approximately 20% charge of scrap used for cooling. And yeah, as I said, CO2 and carbon monoxide are released in that process. So, sorry, I sometimes seem to jump a couple of slides. So, another option for the reduction of iron oxide to iron is, so another option in place of the blast furnace is direct reduction of iron, known as DRI. And whereas the blast furnace has been in operation, around the world for quite a long time, effectively since I think around the Industrial Revolution, 200 or so years ago, the DRI has been in use since I think around the 60s. Might be wrong there, but it's a much shorter length of time. So currently, DRI is operated using natural gas. So this is split, CH4 is split into a mix of carbon monoxide and hydrogen. And those gases, known as reducing gases, both react with the oxygen in the iron ore. You can see the chemical formulae here, giving you carbon dioxide and water. So you ultimately end up with what's known as sponge iron, and the process operates up to around 1,000 degrees C, typically I think 800 to 900 degrees C, and the iron ore is not melted, unlike in the blast furnace. Yeah, you ultimately end up with sponge iron, which is quite reactive, and so if you're going to store that, you need to turn it into a briquetted form, and ideally keep it in an inert environment. And then in terms of another option for steel making, I mentioned before the electric arc furnace. So this can be used with sponge iron, that DRI, as I just mentioned, which comes from a DRI furnace. it can be used with very high levels of scrap. It could also be used with pig iron from a blast furnace. And as I said, you can use very high levels of scrap in an electric arc furnace, which is great for lowering energy demand. So you pass a high current through 3 electrodes, reach very high temperatures around almost 2000 degrees C, and you have a real kind of inherent flexibility there. As I understand it, there's some flexibility also in just going back into the operation of a DRI furnace, much more so than a blast furnace. And then, so I'll now move on to some of the options for decarbonising the industry. First of all, looking at technologies and then presenting a few policy options. So first of all, biomass and CCS. As I said before, one option is to replace the coke in blast furnaces with biomass, but you're limited by that technical limitation of the compressive strength of biomass. It's been found that bioenergy could reduce CO2 emissions from steel production by up to around 40%. So, you know, in terms of very deep decarbonisation, getting down to very small levels of CO2 emissions, or effectively net zero, it couldn't be used on its own. However, it could potentially be used with carbon capture and storage. So you can see this figure at the bottom of the slide here, showing the typical process in an integrated steel plant. So you can see in terms of the rectangles here, we've got the coke plant, sinter plant, and lime plant, and you can see charcoal bioenergy could be used in those, and then could also be used in, as I said, in the blast furnace in the iron making stage. And then some options for post-combustion CO2 capture are also shown here. So in terms of the flue gases from the coke plant and the lime plant, there's options for CO2 capture there. There's, as I said before, emissions from the blast furnace, and also emissions from other places like the basic oxygen furnace, steam generation plant if you use the top gas from the blast furnace for power generation. So there are lots of different sources of CO2 in a large integrated steel plant. So because there are so many sources, it's typically expected that CO2 capture could only be used to capture up to about 60% of the emissions. And if you then account for like about a 90% capture rate, which is typical for, say, amines, amine solvents, then you're looking at around 55% CO2 emissions being captured. However, as I mentioned before, if you were to combine this with biomass, you could potentially get down to very low, or possibly even negative emissions. You can see on the right here the figure showing on land in Great Britain the top 50 CO2 point sources, and then offshore, particularly off the east coast, options for CO2 storage in terms of aquifers and depleted oil and gas fields. So first of all, you could see that the large majority of the CO2 storage sites are in the North Sea. So this, in terms of steel making in the UK, we have Scunthorpe, which is over in Humberside or thereabouts. and then we also have Port Talbot, which is down in South Wales. So Scunthorpe would potentially, could work in terms of being not too far away from CO2 storage sites. South Wales, I think what's been proposed would be to either use ships to take CO2 around to Liverpool, and then I think there's meant to be a storage site in the Irish Sea there. You can see one here. I thought there was one closer, but that's something that I've read. Another option would be a pipeline across right up to Merseyside, which seems it's fairly ambitious from my perspective to be doing that, but it's a big challenge. Scunthorpe would be a better option for CO2 storage. So talking of Scunthorpe, and as we could see on that previous slide, you can see that there's obvious kind of clusters of CO2 point sources, particularly around Humberside area, South Wales. You can see then that there's a big drive to take advantage of the industrial clusters that we have. So one of the proposals is zero carbon Humber, and this is shown here. You can see that what's being proposed is a CO2 pipeline as well as a hydrogen pipeline alongside, stretching between Easington on the East Yorkshire coast out to Drax near Selby. So you have Drax power station. Keedby, I think, is a gas-fired power station run by SSE near Scunthorpe. The British Steel production site at Scunthorpe, and then chemical works at Immingham in North Lincolnshire. So the idea would be that hydrogen would be produced at some of these sites, which could potentially go to be used in power generation, or for providing heat, or potentially as a reductant in DRI. And then also CO2 capture and transport would allow decarbonisation in that route. So this has been proposed recently, and we wait to see what happens with it. So another option then, as I mentioned, is using hydrogen, just pure hydrogen in DRI, rather than using that mix of hydrogen and carbon monoxide, which leads to carbon dioxide emissions. So I'll just quickly explain our project then, because this is really what I've been working on over the last kind of year. So I work on a CREDS-funded project, which is called Complete Decarbonisation of the UK Steel Industry, which is between the Universities of Leeds and Sheffield. And I'm working in particular on a work package looking at the technology options that are relevant to the UK. So there's been a lot of interest in the UK in terms of using hydrogen for heating and heavy transport. So kind of using hydrogen in steel making would fit potentially quite nicely in there. And there's been a lot of development in continental Europe in this area in recent years. So there's the Hybrid initiative in Sweden, which is developing this approach, fossil-free steel making based on hydrogen direct reduction and electric arc furnaces. And then there's also work going on in Germany, and I think maybe Italy as well in these areas. Sweden have recently said that they're going to build a large-scale hydrogen direct reduction plant in Luleå, where they have the pilot plant, and I think they're hoping to get that operational, I think, within kind of 3 years, and have it kind of running at full scale by 2030. So from my perspective, I kind of figured there'd been very little research into the energy system requirements of this approach to steelmaking. And that fit quite nicely in with my background. So just, yeah, to give you a quick overview of this approach. As I mentioned already, DRI typically uses, you take natural gas, methane, and split it into carbon monoxide and hydrogen, and use that mixture of reducing gases as reductants to kind of extract the oxygen from iron ore, giving you the pure form of iron. It's possible to do this just using hydrogen alone. You know, you can use different mixtures of hydrogen and carbon monoxide, and it's possible to do it using hydrogen alone, and it's been done in the pilot plant. There was, I think, a plant in Trinidad, somewhere in the Caribbean, in the 90s that tried to go this way, but the economics at the time didn't stack up, and they had various issues, which I don't think were really related to the fact they were using hydrogen. But anyway, yeah, there's a kind of an overview of the approach in the figure on the right here. So you can see you have an electrolyzer splitting water into hydrogen and oxygen. So you have some waste oxygen there. So an important question kind of longer term would be, what might you do with that oxygen? So use the hydrogen. You need to raise the temperature to about 800 degrees C. So you can do that using some waste heat from the top gas. You then pass the hydrogen into the shaft furnace. It enters at the bottom. You have counterflow with the iron ore flowing down. It extracts the oxygen. It gives you kind of a waste flue gas stream, which is a mix of unreacted hydrogen and steam. And then you, as I said, you extract some of the heat from that, separate out the water, and then mix what you've got with fresh hydrogen. And you just keep running that. Ideally, heat the iron ore up on the way in. You have DRI coming out, direct reduced iron. You can form hot briquetted iron if you want to store this, so HBI there. Or you can do a hot feed straight into an electric arc furnace. And that's the way of kind of minimizing energy losses, because you just take advantage of the heat in the iron. So yeah, it's a very high electricity consumption, and there's been a lot of interest in it in Sweden, I guess partly because they have a lot of low carbon electricity coming from hydro and nuclear. The CO2 emissions of this route are effectively zero. Particularly, you know, if you're using green hydrogen from which is produced electrolytically, powered using zero carbon electricity, and you're also using zero carbon electricity to power the electric arc furnace. It's also possible to use blue hydrogen, which is produced using methane, so steam methane reforming, and then capturing the carbon. However, there would be some fugitive emissions from the methane, and some residual emissions from the CO2 capture as well. But you would certainly make a good kind of transition step towards using electrolysis to produce green hydrogen. So to determine the energy system requirements, I used a thermodynamic process model, used a long-term energy system planning tool with linear programming. It's effectively time series analysis, and the goal of that is to minimize the total cost of meeting the energy demands of steel production. So used hourly wind and solar capacity factors, actually over a 20-year period, and the analysis includes wind, solar, nuclear, flexible generation like CCG, combined cycle gas turbines with carbon capture, biomass with carbon capture, 2 different energy storage technologies, so hydrogen and compressed air energy storage, also electrolysis, of course, for the hydrogen production, and for if you were to potentially want to use the hydrogen to produce electricity, you would either use fuel cells or hydrogen expansion turbines. So yeah, I'll just skip over this. We aggregated the 1-hour resolution data into time slices. So there's 4 time slices in each to represent each month, and they're aggregations of the data for nighttime period, daytime period, evening peak, and late evening. So taking account of the kind of the variability in generation, renewables capacity factors over time. So we use price projections for the different generation technologies recently made by the Department of Business, Energy and Industrial Strategy, BEIS. Also CO2 transport and storage costs, and traded carbon prices also projected by the Treasury. The linear programming problem formulation is here. I won't go into this, but it's safe to say this is all in a paper that is currently under review, and we're hoping to have published quite soon. So some of the parameters for the hydrogen DRI electric arc furnace model shown here. We assume a 50% scrap charge in the electric arc furnace, which is expected to be possible. And this kind of level of scrap charge is being used in steel production in many countries around the world. Some of the parameters in terms of costs, thermal efficiencies, storage efficiencies and costs also shown here. Again, these are all taken from the literature. And the output looks something like this. So this is over 20 years from using data from the year 2000 to 2020, using, as I said, renewables capacity factors, and assuming that we're going to replace the whole UK steel industry with this approach, hydrogen DRI and electric arc furnaces. You can see what happened in the lower part of the figure here in terms of the amount of energy in hydrogen and compressed air energy storage. You can see what's happening with the available wind and solar PV and the steady electricity demand in the upper figure. So the energy demands are something between 0.5 megawatt hours per ton of liquid steel and 3.5 megawatt hours per ton of liquid steel, depending upon the level of scrap charge in the electric arc furnace. Focusing on a 50% scrap charge, then we have a hydrogen demand. To produce 7.2 million tons of liquid steel per year, we have a hydrogen demand of about 700 megawatts, an additional electricity demand of about 430 megawatts. The best combination of generation and storage technologies is also shown in the figure here, in the table here. You can see we would need something like 3 gigawatts of wind, 2.5 gigawatts of solar. Nuclear is just too expensive. About 600 gigawatt hours of hydrogen storage and a small 30, not small really, 30 gigawatt hours of compressed air energy storage. And then about 1.3 gigawatts of electrolysis. I'll just skip over this in the interest of time. It's just how hydrogen storage capacity, well, storage capacity and generation capacity vary with share of energy from wind and solar. The energy system costs, looking at different levels of, if we were to import hot briquetted iron, potentially from other countries, potentially say Sweden, then what would that effect would that have on the energy system cost? Hopefully, I'll be happy to send these slides out. So I'll sort that out with Caitlin and Janine after. just an important last slide on this section then, in terms of the marginal abatement costs. So MAC here, marginal abatement cost, they vary depending upon whether we're thinking about comparing with blast furnace relining, a brownfield site or a greenfield site. And they're shown here using, for different years, based on the generation technology cost projections made by Bayes for the different years going forward. But you can see they're all fairly similar, and they're compared in this figure with CO2 price projections, which are made by the Treasury. And you can see that it's expected that hydrogen direct reduction with electric arc furnaces for steelmaking would be cost competitive with blast furnaces or blast furnace relining within 5 to 10 years, depending upon what actually happens with CO2 price. But I think it's worth saying that CO2 prices have already increased considerably this year. So, I think, it's looking very likely that this approach, hydrogen DRI, could potentially make economic sense rather than going down using the blast furnace and other options, potentially within 5 years. So just laying out some policy options then to decarbonise the UK steel industry. There's a whole range of different options, targets and obligations. So we have the UK government net zero by 2050 target, which was set last year. The Climate Change Committee has recommended that the government set a target for ore-based steel making to be net zero by 2035. I'm not sure that the government has actually, taken that on board yet, but it's a recommendation by the CCC that might be taken on board. So that would be a big challenge. There's things like production and purchasing standards, carbon pricing and tax mechanisms. There's obviously the EU emissions trading scheme, now the UK ETS. An important factor here will be border carbon adjustments. So to make sure that you don't end up with carbon leakage, where we set a high carbon price here, industry just shuts down and moves their production elsewhere. So border carbon adjustments are currently being worked on in the EU. And I think it's essential that we do the same in the UK and try to work with the EU to link the UK and EU emissions trading scheme. So there's obviously subsidies, so it can be direct funding, potential for feed-in tariffs for, say, hydrogen production or CO2 storage, carbon contracts for difference, where companies have much more certainty over carbon price. Then obviously loans and grants, things like the Industrial Strategy Challenge Fund, Clean Steel Fund, public-private partnerships, and the hybrid program in Sweden, looking at hydrogen DRI is a good example of that. And then one other option would be to try and reduce industrial electricity prices in the UK. And the reason why I say that is because it's fairly well known that industrial electricity prices in the UK are relatively high. They're 84% higher than the European median. And there's a few reasons for this. One is that we have less cross-border electricity trading here. And a key reason there is that we have network and policy costs being recovered equally from all consumers rather than being focused on non-industry consumers. So there's potential changes there that could be introduced. This has been put to government a few times by UK Steel and other bodies. So we wait to see what happens here. And this is really important given that electrification will be a key component of decarbonisation. And then just lastly, some views on coal mining in the UK. So yeah, I guess you've all heard about the Woodhouse Colliery proposal in Cumbria. There's a bit of a timeline of what's happened. It was first proposed in 2014, and just to summarise this, it's all kind of been in the news recently because in October, the Cumbria County Council approved the plans for a third time. In January, the government refused to call in the planning application. Then there was such a furore about this that the government finally last month wrote to Cumbria County Council to call in the planning application, and a public inquiry will come next. So yeah, this would be the first new deep coal mine in 30 years, and the intention was that it'll be producing mainly coking coal used in the steel industry. So that's the argument. Coking coal is needed for the steel industry, and that using coal mined in the UK would reduce the costs and emissions associated with transporting coal from the US, Russia, and Australia. I think much of it comes from the US to the UK. And the mine would provide 500 jobs, many of which would go to people in the local area, which has seen really high levels of deprivation. However, I believe that the steel industry needs to move away from using coal in order to meet climate obligations. There's moves towards hydrogen DRI and biomass substitution all over the place, particularly, as I said, in Sweden, Germany, which would mean considerably reduced future demand for coking coal. So potentially, could create a small industry in the area and then leave people out of work in 5 or 10 years' time. So my calculations have shown that reducing coal transport from the US would only reduce greenhouse gas emissions that arise from using that coal in steelmaking by less than 2%. So that kind of saving in terms of the transport emissions is really quite a small component of actually what is coming from using that coal in the steel industry. However, importantly, this will be sending out a message internationally in the same year that the UK hosts the UN Climate Change Conference, COP26, that opening coal mines in the UK is okay. And the precedent that sets, the message that puts out, could very easily wipe out that 2% or less than 2% saving in emissions worldwide. So I also believe that the economy in that area could be stimulated through other means, such as bringing offshore wind to the licensing zone, which is just off the Cumbria coast. And then just quickly, in conclusion, I don't believe that the UK needs new coal mines, and particularly opening a new coal mine would set a very dangerous precedent internationally. The UK government could implement policies that reduce industrial electricity prices, bringing us into line with countries like France and Germany. This would enhance UK competitiveness in steel manufacture and in other areas of industry. We could also implement policies that might increase scrap recycling levels. A strong carbon price will stimulate decarbonisation, but it's really important that this is applied to cross-border trade to prevent carbon leakage and to maintain a basic steel industry in the UK. We have good CO2 storage options on the East Coast, but not really for South Wales. And CO2 capture is difficult at steel sites because of the number of different sources. Substitution of coke with biomass in blast furnaces could only be done up to about 60%. Should say about 40%. biomass resource is limited. National Grid has already said that they believe the biomass resource will largely be used in power generation in future. Hydrogen DRI with green hydrogen and electric arc furnace steel making, I believe, is the only fossil-free option to decarbonise steel production without any kind of clear limitations. And green hydrogen DRI, so using electrolysis to produce the hydrogen. From our calculations, we expect that to be more cost effective than running blast furnaces and buying emissions allowances within 5 to 10 years. And that's it. So yeah, happy to take any questions that you might have.
Thanks, Andrew. That was a great talk and really interesting. Yeah, you've left enough time for questions. Thanks. So yeah, do we have any questions for Andrew?
I can kick it off if that's all right, Caitlin.
Yeah, go ahead.
Yeah, Andrew, thanks for that. Yeah, really interesting. It's really interesting to see such a sort of nihilistic sort of approach to how we decarbonize this industry. And it was really interesting to see sum up a few of those points at the end there, especially hearing it from someone outside of the sort of geoscience, traditional geoscience space as well too. Something I just wanted to ask about though, the idea of removing coal, I guess, from the steel production. While that is a laudable goal, I just wonder at the realism of it. So, for example, if we're going to use wind power to power the hydrolysis for using hydrogen, for example, for steel production instead, each windmill needs about 200 tons or more of steel. So how do we make that steel to make the windmills so we can decarbonize the steel industry?
Yeah. So I mean,
there's the circular argument.
One option would be to use steam methane reforming as a step, so blue hydrogen. It has the advantage of you don't need to worry too much then about hydrogen storage. You can just be doing fairly steady production of hydrogen. It's already done kind of worldwide at fairly big scale. It's been proposed, as I mentioned, in that zero carbon Humber setup. So yeah, that would be an option. But yeah, I mean, I could certainly see the concern that, yeah, very high levels of renewable generation. I think it's key that we increase the use of scrap to bring down those energy requirements as well. But there is a limit to which we can do that to produce high quality, while producing high quality steel. Yeah.
So do you think that the UK steel industry, I guess, such as it is, can, I mean, I guess it's going to take time to move completely away from coal produced steel, but in the interim time when we are going to need to use coal, do you, I mean, this is a very mean question, I guess. I mean, should we not be taking it from our own resources rather than passing the environmental buck on to other countries to get our coal for us while we need to use it?
I personally think that it's opening coal mines at this point is like I said, I think it's a fairly dangerous precedent to be setting. So close to COP as well. Whether or not that happens this year, who knows? I can see the point, but it doesn't do a great deal in terms of reducing transport emissions. I mean, yeah, if we were to go down the route of CCS plus some use of biomass, then maybe in that respect, some mining in the UK would be useful, just in terms of self-sufficiency, if nothing else. But yeah, there's obviously, we have places where we get our coal from already in the, as I said, in the US, Australia, Russia.
Oh, cool. Thank you. Really great talk. Really interesting. Thanks for that.
Is there another question? I have a question. Oh, sorry, Janine's got a hand up. Do you want to go, Janine?
Yeah, sure, thanks. Yeah, I really enjoyed it. Thank you, Andrew. I really learned a lot. It's not something that I know much about, but I was interested to learn about the processes and particularly about the link to policy as well. And I think that that's something that in academia sometimes we feel quite disconnected from, I guess. It's sort of, we can have, I think you sort of made the case really nicely about the technologies there, and the sort of benefits are really quite clear. It's so I just wondered what you thought the biggest obstacle is in terms of trying to achieve this sort of vision of complete decarbonisation.
It's cost. I mean, as I understand it, the steel industry operates on very slim margins. So, and you know, we've all seen that, like, there's always a crisis in the steel industry. So there's always you know, companies looking to sell up or so in that respect, I think there needs to be some kind of support for the industry while it makes the transition to trying out new technologies. Yeah, there's as I mentioned, there's an option there in terms of what we do to try and reduce electricity prices for the industry, to try and bring them into line with what's being paid elsewhere. You know, you could see in that figure we pay, the UK steel industry, I think in 2019 paid about £47 per megawatt hour of electricity. In Germany, they're paying something like £25. In France, about £29. And there are changes that could be made. You know, the network and policy costs for electricity could be lowered for the steel industry and socialised. And this has been proposed, yeah, by UK Steel. It's been proposed by Dieter Helm in his cost of energy review for the government in, I think, 2017. So, yeah, that would be a clear option. I mean, we say that Liberty Steel is in crisis. They use electric arc furnaces. They run electric arc furnaces, and so they use large quantities of electricity. So, you know, they would certainly benefit from lower electricity prices. But I think it's important that goes alongside a strong carbon price, and that carbon price is applied to kind of border flows of goods and electricity as well. So yeah, big challenges, but yeah, I think financial support is key, and maintaining the UK steel industry.
Thank you.
Can I just ask about that, Andrew? Because carbon pricing seems to be a sort of a central thing in what you're suggesting there, and in some ways the most radical thing. And I mean, it would transform our economy, wouldn't it? But I was under the impression there was an awful lot of resistance to that still. And the idea of it happening in the next few years on any kind of international scale, I mean, I'm surprised that you're saying that's possible. I think it should be, but I didn't realize it was that close to happening. So can you comment?
Well, I don't know if it is close to happening. I just believe that, you know, if you want people to stop doing something, you make them pay for it. I mean, I think it's fairly fundamental from an kind of economic standpoint. Yeah, I mean, the steel industry, I think they get a lot of kind of free allowances in terms of what they pay for their emissions in the emissions trading scheme. But those free allowances are reducing. So, you know, they are being exposed to, they are seeing greater exposure to their emissions, and then, you know, paying more of the actual cost of the emissions in the emissions trading scheme. So as those allowances reduce and the cost of carbon increases as is expected, then obviously the industry will increasingly have to cover their costs of emitting CO2.
And is there any consensus on how far ahead in time that cost should be calculated? Because I mean, as I understand it, that's another key thing, isn't it? If you extend it a couple of 100 years into the future, the cost of current carbon emissions are huge. If you only extend it a couple of years, they're probably much less. So is there any way around that conundrum yet?
Oh, I'd never really thought about it to that level of detail. Yeah, I mean, I've heard about like global warming potential, 120, I don't know what else there is, 500 or something. But yeah, I don't know. The ins and outs of carbon price, I couldn't comment on that.
Cool. No, it's really interesting. Thank you.
Thanks.
Okay, I think that brings us to finish around on time. So now's the end of the seminar. Thanks again, Andrew, for a great talk. And thanks to everybody for coming. Andrew has agreed to join us on the Gather Town now, so we can continue this discussion. So if you're free, you're welcome to come and join us over there. I think we can